You also wrote a review on radiation damage, where you compare different radiation sources, electrons, neutrons, and X-rays. Can you tell us a bit about that paper and what was the motivation?
The group I was part of and trying to push in different directions, we knew what the weak points were and we were working on them. But in a way that review was a sort of slight diversion, in that in parallel with the development of all the electron microscopy, electron cryo-microscopy methods, which always looked like it had a lot of potential, there were other people developing other methods. And so, for example, X-ray crystallography had originally used electrons to produce the X-rays by firing electrons into a piece of copper. And then you get the X-rays out and you shine them at crystals, you get patterns. That was back in the 30s. And then they wanted brighter X-ray sources. So they developed rotating anodes where you made the anode move so that it didn't melt when you put the beam in. You get more X-rays. But eventually it was discovered that you could get much brighter, millions of times brighter X-rays out of the synchrotron radiation that comes from electrons going around in circles. Just because they're being accelerated, they produce X-rays, and they're very powerful. So around about, probably about 1980, there was the first synchrotron dedicated to producing X-rays rather than doing particle collisions. Was at Daresbury in the UK. And then Europe got together and decided to build one in Grenoble. That's the European Synchrotron Radiation Facility. And once they've built the synchrotron, they have to decide what kind of cameras and what kind of specimens they're going to look at. And one of the things synchrotrons can do very well is X-ray microscopy. And so there was a meeting at Grenoble that was run by Andrew Miller and Carl Brandane, who were the biological sciences director and ex-director. They were running the meeting, and they wanted to know whether it's a good idea to build an X-ray microscope. And because I had come from X-ray crystallography and I was doing electron microscopy, we knew all about it, radiation damage and so on. I had published papers about it before. So I was asked to go along and give a talk explaining about how much radiation damage you get with electrons, how much you get with X-rays. And the bottom line was that electrons are 1,200 times better than X-rays. And so I gave this talk, and there were 50 people in the audience. They all were X-ray microscopy people. They were really very angry because they wanted 5 or 10 million euros to build their synchrotron beamline for X-ray microscopy. And I'm telling you, this is a really bad idea. You can do quite good X-ray microscopy, but not on molecules and atoms, but on cells and so on. They did get their beamline in the end, but because they didn't understand this, I thought, well, if 50 clever physically oriented scientists don't know this, perhaps it would be a good idea to write a review. So I thought I'll write a review just comparing X-rays and electrons in terms of radiation damage and resolution. Although I'd published papers before about it, obviously they hadn't noticed them and so on. So I wrote this review, and then during that time, there's another journal called Neutron News, and we used to do some neutron diffraction as well. That's slightly useful in structural biology. And because we did one experiment and published one paper in 1984, every few months I still get a journal called Neutron News. And while I was writing this review about X-rays and electrons, Neutron News arrived with a center. You opened it, and it had a big full-scale table, every single element, every single isotope, telling you its lifetime and how it interacted, neutron cross-sections, elastic, inelastic, and so on. And so I thought, maybe I should expand it to be electrons, X-rays, and neutrons. And my surprise was that not only are electrons 1,200 times less damaging for the information you get in the images than X-rays, they're also 3 times less damaging than neutrons, even though neutrons have a very weak interaction. And so I thought that was very good. So after having written that and published it, I thought, well, maybe we should, since electrons are so clearly better, perhaps we should do some more calculations. So it had added into it, if you then now focus on electrons, what is the genuine theoretical potential? So assuming all practical problems, which is what we've been working on, microscopes, vacuums, sources, detectors, supposing they all work perfectly, and we had phase plates and so on and so on, how well would it do? And it came out that you do very well. And so after writing the review for a different purpose, we decided, okay, we would give up all crystallography and switch entirely into the single particle electron cryo-microscopy. So from about 1995, 96, that's what we did. And for example, people came to work. There was a visitor called Sriram Subramaniam, who now does electron cryo-microscopy. He came and we said, okay, in 1 year, we're going to do 10 structures, all at atomic resolution by electron cryo-microscopy. And then we started, but we discovered, of course, that there were quite a lot of problems that needed to be solved. And that took another 15 years or something like that. But, you know, the essentially the vision was there and the theoretical underpinning was there in that review. So it was even though it was done for a different purpose, it served a number of purposes afterwards.
And so do you think we still need synchrotrons for structural biology, perhaps for small molecules?
Do we need synchrotrons? Yes. And not only for small molecules, actually. They have been greatly improved. I mean, the intensity of the X-ray beams or any electromagnetic radiation that you get out of synchrotrons, compared to, say, 1980, they have been increased many millionfold. So the quality of the X-rays you get out of synchrotrons is really fantastic now. And it's still being improved. So nearly all the synchrotrons in the world, they've been running for, you know, the state-of-the-art ones, they've been running for 20 years. Periodically, they shut them down and they rebuild the magnets and the focusing elements to make it brighter and brighter. And so at the moment, the ESRF, the same one that I went to that meeting about, it is currently being upgraded. And that means that if you have a crystal, and let's say in 1960s, it would take you months to collect one three-dimensional data set of all the diffraction from the different angles in a crystal. That you can do now in 1 second instead of months. So you can collect, if you have a crystal of a biological structure you're interested in, you can solve it in minutes now. And so one of the big uses of X-ray crystallography at the moment is if you are looking to develop a new small molecule drug, let's say an oral pill that you take to cure you of, stomach ulcers or heart problems and so on. Usually the biological target, which would either be a human protein or a bacterial protein if it's an antibiotic and so on. And let's say you're analyzing that protein, you make a crystal of the protein, you can then add to the crystal the drug that you're trying to develop and determine in a minute or so, you can determine the structure of the enzyme with your small molecule binding to it. And that small molecule might either block the activity of that biological molecule, or it could activate it, depending on what it is that you're trying to do. And then once you've got one molecule, the pharmaceutical companies, they usually make hundreds, if not thousands, before they get one that has all of the qualities that they're looking for to make a really good treatment for some human disease or ailment and so on. And so the structural biologists would like to determine the structure of hundreds of these compounds. And the great thing about synchrotrons, the brightness of the X-ray beams is so big, and the detectors are quite good, they can always be improved. They can do 300 structures every day. Whereas with electron cryo-microscopy at the moment, it's about one structure per day. Now, obviously, you can make the detectors bigger and faster, and the electron microscopy will get better and better, but you'll still have this advantage that once you've got a crystal, it's very quick to do different complexes with different small molecule ligands. So synchrotrons will just get brighter and brighter. Probably we have enough of them. It's just that they all need to be continually improved. And then one of the new let's say, directions that have been developed. Instead of having a synchrotron that makes all the electrons go in a circle and produces X-rays coming out in all directions, or other electromagnetic radiation coming out in all directions, there are now linear, what they call free electron laser synchrotrons, where you accelerate the beam using a radio frequency magnetic wave to accelerate electrons, and as they go faster and faster, this is Wakefield essentially wave. So you get, along with the electrons, you get the X-rays that go with them, and then coming out of the end, you have a very, very much brighter and more powerful X-ray beam and an electron beam. And of course, the electrons, you can just divert them away with an electron field, and you get a pure pulsed electron beam. And that these are even more bright than the let's say what they call third generation synchrotrons. But it's a technique and a brighter source looking for problems where it can be used to solve. So the synchrotrons will never go away. They'll always be needed. And in structural biology, electron microscopy is still not producing every year, let's say, for every electron cryo-microscope structure that is deposited in the public databases. Of course, it could be done by no other method. You're getting at the moment 8 or 9 structures being deposited by X-ray crystallography, although many of them are sort of related structures, so they've been repeats with slightly different ligands and so on. So the idea is that as the methods improve, the X-rays will get brighter, the electrons will get faster, the detectors will get it. We think if you look at the statistics and how people are deciding to spend their time in the structural biology field, it looks like in about 4 or 5 years, the number of structures being deposited will be about the same from electron cryo-microscopy and X-ray crystallography. And then after that, so that's 5 years from now, we already know probably about half of the structures in biology. We have atomic models, either for the structure you're interested in or a very closely related one. So probably within 5 years, you'll find that most of the landscape of structural biology has been mapped, and there are in the databases examples of nearly all the biological structures you'll be interested in. So for example, Bacteriodopsin now, there was one structure in 1990. Now, if you look in the database, there's 200 of them with different ligands, different mutants, different intermediates trapped. And many of the enzymes, you'll find that there's 1,000 different examples of them. So as the methods get more powerful, you can, instead of just saying, I would like to know the structure, and you get one structure and it takes years, now you can look at the structure, how it behaves, what its mechanism is, how it interacts with other molecules, and so on. So there will be a broadening of the, let's say, the landscape and the ambitions of the structural biologists to tackle problems that are in addition to just finding out what the basic structure is.
What do you think about facilities such as the CM01, the eBIC, and the ePSIC? How do they play a role in the community?
As the use of X-ray diffraction grew in the structural biology community, both for structural biology and for chemistry and physics, material science, and so on, it became clear that people couldn't have a synchrotron in every lab because they cost £400 million to build it. And so from about 1980s or 1990s, the idea of having national facilities. So in the UK, we have one synchrotron. France has one synchrotron. Germany has one synchrotron. Europe has a bigger synchrotron. America has about 3 or 4. Japan has 2 or 3, and so on. So there are probably 20 or 25. Italy has one, and so on. Synchrotrons in the world that are all national or regional facilities. And so in the UK, they were probably the first one. 2 scientists here, Dave Stewart, who is based in Oxford, Helen Sable, based in London. About 10 years ago, they decided actually that electron microscopy was also beginning to become more expensive, and that they couldn't justify one microscope costing £5 million in every lab. So they advocated and succeeded in getting funding, some grant from the Wellcome Trust, which is a UK-based charity, to buy the first high-end 300 kilovolt electron cryo microscope. It was going to be based at the synchrotron, and they would use the management system they had developed over 10 years for applying for access to the synchrotron beamlines. They'd use the same thing for electron microscopy. And particularly Dave Stewart advocated, as part of an upgrade to the synchrotron, where they were building one long beamline. So one of the 30 beamlines was a long beamline, and it's there. And so at the end station for a long coherent X-ray beamline, they made a big building that was also for electron microscopy. So several thousand square meters. And half of it was supposed to be for electron microscopy tied to physical sciences. That's ePSIC. And the other half was tied to the biological sciences. And Wellcome, when they funded the first microscope, said, you cannot have a national facility with one microscope, because if it goes wrong, it won't work. You need two. So they were persuaded that they applied for one and they were given two. And now, of course, because it's such a successful and popular method, two is not enough. And so they're now up to 5 plus 1 or 2 other microscopes. So they've got about 7 or 8 in eBIC. And it is now, quite a successful, fully integrated with the synchrotron, the same beamline allocation panels. And so the idea now, I think, is that the very expensive microscopes that are successful, and many people who are just the users, they don't want to know anything about it. They just want to get, here is my protein, I want the structure, and they don't want to know anything. They're just users, just like having your DNA sequenced in a plasmid and so on. And so these national facilities are here to stay, and many countries have decided to co-locate them with the synchrotrons because of the common underlying infrastructure to manage it. And so Stanford in the USA has got an EM center now alongside its synchrotron. Brookhaven in the east coast of America thinking of doing that. But there are also national centers for EM that are not at synchrotrons. And again, we don't know quite how things will develop, but it's a good model basing them at synchrotrons. And so here in this lab, we have 3 of these high-end microscopes. And we are debating, is it a good idea for us to be running a big facility like that, or should we integrate it with other national facilities? And in the UK, because the UK has been a leader in this type of electron microscopy, one of the leaders, there are now 20 or 21 of these high-end microscopes. So 2 in Leeds, 1 in Glasgow, 1 in Leicester, and so on. So they are distributed, but the biggest number are in Oxford. They have 6 or 7 of them there.